Hello, everyone, and welcome to my talk, Elastic Scalable Java Apps and Microservices with EclipseStore. I did this talk already yesterday, but I think for now I could shorten the first part a little bit, and that enables me to give you a better impression of the cluster and the cloud or cluster front end of MicroStream. But yeah, let's step into it. Yeah, I think Marcus introduced me enough, so I will skip that. And some of you already know me. So the first topic for today, what is EclipseStore? As I said, I will shorten that a little bit because you already know what EclipseStore is and how it works and so on. And that's the part where I can shorten that a little bit. But as I said, at the moment when we talked about EclipseStore, a lot of people ask for scaling and how to handle this if data increase and stuff like that. And I'd like to take you with me to the journey of what we found out during our research of scaling and clustering and stuff like that. And I want to clarify a lot of terms that comes with clustering and cloud and services and so on. And we want to clarify that, and after that, I will explain you the ideas of the EclipseStore, how is the architecture and how does it works, and how you can use this. Then we go to a live demo and deploying an application to the cluster and see what's going on. And as I said, this is the part which we can a little bit extend in this meeting to see what's up in the cluster. The roadmap of the cluster, I think I already talked about that, but yeah, I will repeat that today. Yes, as I said, whenever we talk about EclipseStore, a lot of people said, "Oh, that sounds great," and but what about scaling? And as I said, we do a lot of research in the past, and we found a lot of terms. So, and I listed them here. There are a lot more, I'm pretty sure, but we found something about horizontal and vertical scaling. Then cluster replication was all the time, especially the term replication. It's quite interesting. Then we found some stuff of stateless and stateful and consistency, especially the eventual consistency stuff, async and synchronous access to a cluster, and a lot of more stuff is going on and a lot of more terms. And the more we thought about, the more we find out that at the beginning, there are two very basic decisions you have to make. And the first one is to make the decision, how do you want to scale? Do you want to scale horizontally or do you want to scale vertically? And we will clarify that two terms and what does it mean in exactly. And the second part is scaling for what reason. That's quite important to know. What should be scaled? Is it data scaling or is it scaling for maybe high availability? And what is the difference to high availability compared to fail-safe? It sounds in some way it sounds the same, but in fact it's not the same in the real world, I would say. And these are the two main terms we have to clarify, and then we go further and see what's going on next. Okay, so that's what I said. So we have to make a decision to see, okay, what does data scaling mean? And normally at the moment we all the time talking about sharding. So that means it looks in a way, I would say, like this. So that means I have a list of, let's say that's our employees or customers, doesn't matter. And we have a list of them on one EC2 instance. And if the list is full, we create a new EC2 instance with some more. And if this EC2 instance is full, we go to the next and so on and so on. And normally I think that's an easy example of data sharding. And this is the idea how it could work basically. And it's made for a continuous increasing amount of data. And this is one type of data scaling. In my opinion, it's not the most important part because there are a lot of solutions that prevents you from data scaling. I'm pretty sure there are some companies on the market, they they have to handle millions and billions and some more data, but most of the companies are they have other mechanisms to prevent data scaling. For example, you use an archive mechanism to do archiving stuff every night. For example, when the data is older than 2 years, for example, then you you migrate or you move the data to an archive or something like that. So that's what I want to say. Most of you are able to find a better solution than data scaling, because it's also a highly complex topic, and it's quite difficult to solve that. Okay, that's data scaling, but the next part would be high availability and fail-safe. Let's talk about fail-safe first. Fail-safe means most of the time keep the impact as small as possible if something fails. Fail-safe does not mean prevent the data, prevent some of the architecture to fail. That is not what fail-safe means. Fail-safe means to keep the impact as small as possible if something fails. And high availability means keep response times within an acceptable limit, whatever happens to the system. And that's, I would say in some parts that's the same like fail-safe, but because some instances could fail or at the end, but it could also be an increasing or abnormal amount of concurrent accesses at a time. So and that could be possible. And I would say if you guarantee a high availability, you will be fail-safe at a time. I think that's where both terms comes together. So when you solve high availability, you will be fail-safe also. And when we talk about that, we talk about replication. So, but what to replicate, I come to that later. Okay, so I think that's the two reason when we talk, or these are the two elements when we talk about scaling. Then we mean data scaling or scaling of computing or hardware resources, I would say. And it could look like this at the end in a quite easy way. So we have multiple pods with data in it, and there is one load balancer which routes to the machine, which can handle that in an acceptable amount of time. So, but there was a third topic regarding that horizontal and vertical scaling. And the basic approach or the basic definition is when we talk about vertical scaling, we talk about increasing CPU and RAM to a certain limit. So that's easy. What we see. The advantages of vertical scaling is it's quite easy. There are no big issues, so you can keep your programming, you can keep your code, and everything is fine. Just increasing the CPU and RAM, and you are good to go. And the next point, I think it's the same. It's cheaper at the end. So because just increasing CPU and RAM will cost you hardware resources, or will cost you money for hardware. And it's the same, or it doesn't matter if you're increasing from 2 CPUs to 4 and 8. You could also increasing new hardware resources like EC2s with 2, 4, or just using 4 EC2 instances with 2 gigabytes of 2 CPUs, for example. It's the same at the end. You will have the same hardware resources at the end, and it will cost you the same. But it's cheaper at the end on human resources and personnel costs, I would say. And I think that's exactly the point. And there is a great thing on vertical scaling when we talk about fail-safe. So if fail-safe of 99.99% is okay for you, then you could choose AWS, because AWS guarantees you that availability on an EC2 instance, and that's great. I think that's okay. And let's say if something fails, you could restart your container, and that's it, and the application is up again. And I'm pretty sure for a lot of companies on the market, that's totally enough in case of fail-safe and high availability and so on. But of course, you are also right when you say, okay, the technical limitations are there, so that we are not able to increase in an unlimited way. So we are limited by the cloud architecture, for example, or by the policies of the cloud itself. And of course, you are also right when we say high availability is not covered. That means the more concurrent user we have on a system, the more decreases the concurrent users, is decreasing the response times of my application itself. And that's a problem. So we have to find a solution for that. And that's why we come to the horizontal scaling. It's basically increasing the number of hardware units within a structure. It could be some containers within Docker, for example, or it could also be nodes within Kubernetes. That's basically the same, I would say. It's the same architecture. On the pro side, we have no limitations for scaling. Of course, we have, and also the high availability is solved in that specific case. But on the con side, we have costly infrastructure and of course staff costs. And it's highly complex to understand what's going on in the background and how does it work and all the stuff you have to configure to create an horizontal scaled architecture. But some of you might say, no, it's not. It's not expensive and it's quite easy to use. Also the horizontal scaling part. This is because of these two words. So when we talk about stateful and stateless, then I would agree at the end when we talk about stateless services, then I would totally agree to say, okay, quite easy. And what does it mean? Basically, it is a server is able to store an information, or if a server is able to store information, then we're talking about a stateful server. So that means whenever we call the server and say, okay, let's hand over a name or something like that, then these specific server within my horizontal scaled architecture becomes a stateful server, because you are not able to force the load balancer to route you to a specific server, and that's why it becomes a stateful server. And that's what I want to say. No matter how big or where the information comes from, or that doesn't matter. At the moment when you store data within a server, it becomes stateful, and it's hard to handle, I would say. And it's also sometimes the whole architecture. Let's imagine that we start a server and it loads data from a database. Then the server represents the state of the database itself. So then we have a stateful system at the end, or a stateful architecture. And as I said, with the stateless point, it's an easy node replication, right? So let's imagine we have one node to create a report. We could have thousands of nodes that creates reports for us. No matter how many concurrent users want to create a report, we can create more and more, and this is quite easy. On the stateful side, we have to replicate the data. So we have to find a situation, or we have to find a solution to replicate the data to all the pods in our architecture or in our cluster. This is highly complex, and this is the point where things becomes complicated. But before we get into it, let's talk about hardware. We didn't talk about hardware, and sometimes that's also interesting. So in my opinion, I want to just show you two different hardware resources you can use for clustering stuff. And this could be a Docker container, for example, or a Docker itself as a system, and you could have multiple containers in it, and with one load balancer, of course. And in the end, you will have one EC2 instance around them or under the Docker system. So because the Docker runs on the EC2 instance, and we have that container on it. But in the end, this solution is again only a solution which runs on one hardware resource. There is no horizontal scaling, because Docker is not able to to spread Docker over multiple hardware resources. That's not possible. So we have one EC2 instance, and we're only able to vertical scale this one instance. And if you want to have more, and if you want to span the infrastructure over multiple hardware resources, we have to use Kubernetes. And then it's a little bit different. So we could have our same structure. We have a load balancer. We have multiple instances of our server. And then these server pods are running on different EC2 instances. And there is one Kubernetes which wraps all the hardware resources and takes care about resources and scaling up servers and stuff like that. This is made by Kubernetes. And there is another point which is very important on that two systems. Only Kubernetes is able to scale in a dynamic way. So that means whenever you want to have more containers and more load balancers, and if you need a system that makes the decisions that you need a new server because all the other three are totally full of concurrent users, I would say, or concurrent accesses, then Kubernetes is able to create a fourth one and loads new EC2 instances from the background as a hardware resource and stuff like that. But Kubernetes itself, it's highly complex, I would say, a lot more complex than Docker, also on the security side. And but in our specific case and in our, as I said, the journey to make MicroStream or EclipseStore scalable, we have to use Kubernetes because, we need it. We need those features. That brings me to the replication part. We talked about replication, and especially when we have stateful servers. And then we have to make a decision, and one of the first important decision is what type of replication should we use, or what type of replication do we need? And there are two different types to write data. One is the async way to write, and that makes writes non-blocking. And we have the synchronous way to write. What that means at the end is when we choose the async way, so we do a request to write data, and we get the response back, because the server does not wait to replicate all the data to all the other nodes. This is made in the background, and you will never know if this works as expected. So you send the request, and directly you get back the answer, and that's it. That is the meaning of async, and it's the complete opposite of in the synchronous way. So that means you call the request, and then the replication is made in the background, and after the last node is replicated, or after all the informations are replicated, you will get the response back, and that leads to a bigger latency, of course, or more latency than in the async way. But I would say, in my opinion, most of the time we have the asynchronous variant in most of the clusters. Then next point is also quite important to decide or to make a decision whether it should be a single leader, multi-leader, and no leader architecture. And the description is behind the word that there is single leader means that it is one writer node that makes things a lot more easier to handle. And that means there is only one node which writes the data, and from this one node, the data are replicated to all the others. But there are other solutions with multi-leader and no leader. No leader means all the nodes are able to write, but that leads you to some other problems with data loss and data less and stuff like that. It's difficult, I would say. In our specific case, especially for EclipseStore, we decided to use the single leader architecture. That's what most of the people need. What strategy regarding strong consistency and eventual consistency? And that's why we already talked about async and synchronous. On the async variant, we mostly have we mostly have the situation that we have to deal with an eventual consistency. But it's not only because the async stuff. It's the same. Let's imagine you write down any information to the server, and yeah, half a second later, another user calls for let's say products or stuff like that, and it's not guaranteed that he will get always the latest data. And that is what eventual consistency means. That provides you low latency, but a possible stale data. So you will not be able all the time to get the latest data. That's that. And the difference or the opposite is strong consistency. In that specific case, it's guaranteed that you always get the latest data. So, and this is the same on our cluster. We running on, or we using the eventual consistency. We choose the eventual consistency at the end. So you see, there is a lot of stuff going on when we talk about clustering and scaling data, a lot of things we have to deal with. And this is only the theoretical part, I would say. There are a lot more stuff is going on the Kubernetes side, on the configuration side. You have to make a lot more decisions regarding infrastructure and so on. And then we are still not talking about how to handle backups, how to monitoring all that stuff, how do logging and security. That's a really huge topic that we talk. And yeah, let's see how we handle that. So the idea of the MicroStream cluster was central point for hosting your application, and be more precisely to hosting your data provider. So that means MicroStream or EclipseStore itself. It's a database technology, I would say. It's an in-memory storage, and so we need a central point for hosting that data provider. And there is another point we want to talk or we want to have in the future, to provide a hosting point for different types of applications. So in the future, there will be maybe the possible to host Vaadin application or Spring applications. What is totally on you. And we want to have data replication within the cluster. And the meaning, and the point is to do this in an automatic way. And yeah, of course, one of the biggest points is hiding you from the complexity of infrastructure. So you should not, you don't have to deal with security. You should not deal with Helm and dealing with Kubernetes and stuff like that. Just using the front end we provide, and that gives you all the possibilities you need to handle that. And also providing you monitoring, logging, backup out of the box. That's what was the idea of the MicroStream cluster as a service. So, but the biggest question was, EclipseStore is still a framework, and yeah, that's for sure. And how to create a server out of it? How to create something which runs on a server as and we thought about a relational database. And let's imagine, okay, we have to install that database as a service, for example. We had to create tables and constraints, and we had to create the JDBC connection and define queries in our application. And then after all that stuff, we call the queries and use the queries in our application. But on the other side, when we talk about a Micronaut data provider, and when we talk about a Micronaut data provider, we talk about a Micronaut application which contains EclipseStore as a framework and provides REST interfaces to everyone within your infrastructure. And then things becomes quite similar. So that means we have to create a setup with Micronaut, Helidon or Spring. In our specific case, we have to create a data structure, but instead of doing that with SQL and instead of creating tables and constraints, we're creating a data structure in Java, and that's part of our project itself. And then we create REST interfaces. And I think, in my opinion, it's quite similar to defining queries, because we doing streams within our REST interfaces, and there is also things are quite similar. And that brings us, or that it gives us the idea to say, okay, let's create a Micronaut data provider to create the data to everyone, and just provide a front end to upload that specific data provider, and the cluster itself takes care about data replication in the background. You only have to decide how many pods and nodes should be available, and that's it. So that means you create, at the beginning, you create a Micronaut data provider which runs out of the box directly on your system, and just after changing small things, you will be able to upload it to our infrastructure, and we do all the replication stuff automatically for you. That's the idea behind. And at the end, you will get something like that. It consists of there is a Spring, Micronaut, or Helidon template you could use. EclipseStore is already in place with the MicroStream cluster API to handling the cluster, the replication in the background. And there is a REST API, which is quite standardized, and you have just to create your REST endpoints to provide the data to everyone. And that brings you another advantage. You create, as sometimes I say, you create your own database, right? And this is kind of like on the relational databases, you sometimes have those views, for example, or the stored procedures at the end. And this is quite similar to this situation. At the end, we have our REST endpoints, and you will be able to add your own business logic to these REST interfaces. And yeah, that would work great. And let's see how this works. So let's switch to my IDE. I created one example project for you. And this is, by the way, the same project we also use within the demo now. So we see the DB class. I think Florian shared the code already. And we usually use the embedded storage manager here in that specific case. But instead of using the embedded storage manager, oh, you see only black? Okay.
No, we can see the screen. It's okay.
Okay, great. Instead of using the embedded storage manager, we use that cluster storage manager. And the way to initialize it is quite similar. But the special thing is that this cluster storage manager is able to communicate with our cluster infrastructure in the background to do a proper replication at the end. And we still need one root entry or one root object on top of the object graph, as always. And the complete handling of EclipseStore in that specific case is totally the same like you use it with an embedded storage manager. We have our data root. We have the same data structure in the end, which is the data structure of a standalone application. The only thing which differs a little bit, or even not, is the controller class. So this is the controller class, which looks like a Micronaut straightforward controller class. There are several HTTP methods like get and patch and post and stuff like that. And this is the stuff I talked about, which is quite standardized. So everybody knows this, how to use. And you have just to add your business logic within those REST interfaces. And yeah, whenever you call the store method at the end, this stored part will be replicated through all the nodes within the cluster. And how this works, I come to that a little later. Okay, so this is how the project itself looks like, really straightforward. And on that point, we move on to, let me just double check, yeah, so, okay, let's skip that. We do not need that. Okay, so when we have that project like this now, we are able to skip to our MicroStream cluster front end. So this is the test cloud. This is because we changed something in the background. We changed the architecture a little bit and compared to the already available cloud. And when we move on to the platform overview, it looks different, like the overview before. That's why, or the reason for that is we separated the platform from the cluster itself. That means now you could have multiple clusters. You see there are 2 clusters. One is in Frankfurt and one is in US East, Ohio. And that enables you to have multiple platforms. And you need only one platform, and you could have multiple clusters here. When you click on Add Platform, you could choose what kind of cloud provider you want to have. In that specific case, it's an AWS. But later on, you will be able to choose Google Cloud or Azure. And then you could choose the region, and you could create a platform. I've already done this. So we already have a Frankfurt platform here. It needs a little bit, it needs around 15 minutes to create a proper platform. So we save that time now. And after that, we click on Add Cluster. And that brings us to a front end, which enables us to choose a cluster tier. And for the moment, we have 3 different cluster tiers. We provide 3 different cluster tiers, a small, medium, and a large one, which differs from the minimum node count to the maximum. So at the small, we are able to run 1 to 2 replications. On the medium side, we are able 1 to 5, and on the large one, we are able to run up to 10 replicated nodes at the end. And let's choose a small one. And next thing we have to choose is the size of our nodes. So, and the node itself, it's the underlying structure or hardware resource to our project itself. So that means you have to choose how big is, or how much RAM do you need, or how much CPU you need. And in my specific case, it's totally enough to have a 500 millicores machine. We call it micro, with 1 gigabytes of RAM. That's totally enough. And we have a total storage space of 20 gigabytes. I think that's totally enough. And we are able to choose the amount of nodes do you want. So that means with that specific small, so we are able to have up to 2 node counts, and we could do that. We could choose 2, and let's click on Next. Then we have to add the cluster name. We have to choose the type of application we want to cluster. In my specific part, it was a Micronaut application. Then we need the URL of the GitHub to help me to pull that from the Git repository. We have to add the branch itself to choose the right version of the application. And that's it. Let's click on Next. That enables us to create some backup specifications, maybe the backup interval and the amount of the last kept backups, for example. We have to use, or we have to choose a way to authenticate the access to the cluster itself. And there is another possibility to create an AWS private link. For all you guys that already have an AWS infrastructure up and running, and you create a private link, that means that the data from our cluster goes straight directly to your infrastructure without touching the external internet. So and that's what a private link means. The data goes directly without touching the internet. Okay, next and last but not least, the proxy settings. These settings are also quite interesting. We have to make a decision. Maybe you remember we talked about the single leader architecture. That means there is only one node which writes the data, and we have to find a way to separate the REST calls. And we have to ensure that the REST calls that are writing data goes only to the writer node. And we could do this in three different ways. The first way is to use the HTTP methods to say, in this specific case, we would say put, post, delete, and patch goes straight to the writer node. And But we could, instead of this, we could choose a specific URL path to route the requests. And as an example, we could say every URL with an edit in it, or after an edit, will directly goes to the writer node. And there is a third possibility to add a specific header value to ensure that every request which contains this header value goes directly to a writer node, or to the writer node. Okay, in my specific case, I'm totally fine to use the HTTP methods, and then you can click on create, and that's it. You will see this is the new configured cluster, and you will be able to start this. Instead of starting this, that needs around, I would say, 6 to 7 minutes. I already created one, and this is the cluster which is already available. And let's jump into the details. And now here you can see all the stuff I promised you: the monitoring, the logging stuff, and some more configuration or possible configurations. Basic and backup configuration, we already talked about this. I think more important is the monitoring itself, that provides you all the metrics you need, need to know what's going on my system. You could choose the different pods within the cluster and what they are doing, and what is the CPU usage in millicores, the RAM usage, the bandwidth in kilobytes per second, the throughput, and so on. That's quite interesting to see, and I think that's totally necessary to have that, to see what's going on. And it's the same on the logging side. So that gives you the possibility to see all the logs of your different nodes. And you see these are the logs of node 0. There is only one node in that specific example. And these are all the logs of the node. And that's important. If something goes wrong, you have to check what happens there. And yeah, some more informations are interesting. Okay, there is another tab there. It's an uptime configuration. So we planned that we add kind of like an uptime scheduling. So you will be able to decide, okay, my cluster should run between Monday and Friday from 8 to, let's say, 10 p.m. And that brings you to the situation where you can decide, okay, what is especially for development purposes, it makes sense to have that, that you can have a dynamic scaling of your cluster itself. Okay, so at the end, if the deployment works, you will get a URL. This URL is the right one. And that brings me to a small example. So there is, I created a small JMeter example, just to give you an idea how this could work. I already added 1,000 products, I guess, to that application, and now we are able to call them. It's already empty, and this is the HTTP request. Okay, and in that specific case, we said, okay, we have 5 threads that runs at a time, and all the time they call the get method of that 1,000 products. That means every time we call it, and we start with one thread and see what happened when we call them, and directly you see the graph at this time, and you see, I think it's a little bit hard to see. We have a response time of 48 milliseconds. That's okay, I would say. You have to imagine, maybe we could stop that for a short moment, and then I give you a short idea of the data itself. You see, this is what the data representation is. These are this is one row of data, I would say, and based on that we have 1,000 exactly. You see that is a little bit of data, And this is also the reason why we are not able to increase the base response time of 48 in that specific case. Let's try to increase that a little bit. And now you will see that my local machine here is working quite hard. So let's choose 5 threads and let's run this. And this will increase the amount of calls. At the moment we get, let me just check, 100. No, that's the throughput. So we have 28 responses per second for the moment. And when we have a short look to my cloud infrastructure, and let me just refresh, you see that this is what's going on the node itself. So we have in use 71 milli CPUs and 181 megabytes of RAM for that amount of data. But the problem is that my local system is not able to handle the amount of data which comes within, so that my bandwidth of the network is not high enough. And therefore, we get a result of, let's say 341. You see that milliseconds, or a little less. So where is it? So we have a response of 143 milliseconds on the call. But this is the reason for that, is that my local bandwidth is not high enough to handle that amount of data. Okay, so you see on that very tiny machine, there is a lot of possible traffic possible, or there is a lot. How to say? Yeah, doesn't matter. So your machine can handle a lot, I would say. Okay, let's jump back to the presentation itself, just to show you a little bit more in detail the architecture, how it works in the background, and then we move on. So whenever we read our data from the cluster itself, it goes to the load balancer, and the load balancer makes the decision which node can serve the data. And also the writer node is serving the data if it's possible. And this is how it looks like when we store data. The load balancer makes the decision, okay, this is a write request. It goes to the writer node, goes to the storage and to the backup node, and will be replicated at the end via an Kafka message service directly to all the replicated nodes in the end. And this is how it basically works. Okay, these are the features. I'm pretty sure we talked about that. We already talked about that. And this is the roadmap for the next upcoming versions. So as I said, we want to support Azure and Google Cloud also, like we do it now with AWS. There is one framework which is not available now. It's Spring itself. So we will support Spring in that case. For now, we support only Helidon and Micronaut. But it is not a big issue to provide the same with for Spring also. Then we planned to provide an advanced REST and CI/CD Jenkins deployment, so that you can deploy it via REST and via Jenkins or GitHub Actions. This is what is planned. And another great feature would be the auto-scaling feature. That means for the moment, when you choose 3 nodes, you will get 3 nodes. So the nodes will not scale up and down, but we plan to implement an auto-scaling feature. That means if load traffic is going on, then only 1 node is available, and if traffic increases, that the cluster will scale automatically up to your maximum amount of nodes. Okay, we already talked about that zero scheduler, and yeah, there are some more upcoming types of the cluster, but this is future stuff. Okay, yeah, that's all from my side. Now it's up to you. Ask as many questions as you can, and the first one I see is clustering is an enterprise feature. Yes, it is. It is definitely an enterprise feature. Yeah, that's what I could say. So there is that's also interesting. Yes, there will be the possibility to have that with an on-premise solution. So we are working also on a solution that you can install on your side, so via Helm chart and stuff like that, and you will get a lightweight front end also, which looks quite similar to that front end we have seen it in the presentation. That enables you to configure and handle your own cluster, and so that means you will get all the Helm charts and all that stuff to install it on your own Kubernetes infrastructure to have that cluster on premise. That's what we plan to do. But for the moment, it's only available on that SaaS platform. Okay, some more features or some more questions, I would say. Features are also great. So no, it's not. So the cluster is doesn't support sharding. That could be, or this will be a more advanced feature for the future. And I won't promising that, but we are still working on a sharding solution. But let's see what's upcoming in the future. I already asked it in another question. What about quarks or Quarkus? That's interesting. Not sure, but we already talked about that. But yeah, it's not forgotten, I would say. Let me just have a look on that. You're right. Yeah, it's not mentioned here. I have to double check this. So I knew we talked about that, but I have to check the issues and so on and the roadmap. Then, hi Christian, inform us on security ransomware. Can you be more precisely, Repco, on that?
I do it live. It's just the biggest worry about the data is that you get a thing with ransomware, and then that has to be dealt with. Can I be sure if I do this product that this is not an issue?
Okay, so maybe some of my colleagues could help a little bit regarding ransomware. So there is something I missed, I guess. So
Repco, can you please repeat your question?
If I put my data in this environment, my biggest anxiety is that it will be a target of ransomware. So I want to be sure that it's duplicated, never be an issue of worry that the data is on some kind of threat.
I think it means all over the security stuff on the server or on the cluster itself. So I think there are two different layers of security in that specific case. So the first layer is the Kubernetes layer and everything what is running on AWS. And this is all that stuff is covered by AWS. Most of the time we are using the we are using the best secured software at the end, which is provided by the cloud providers. And there is a second layer, I would say it's the application layer. So that means on the Micronaut side, for example, you have to do it by yourself. You will be able to cover everything in case of for the security stuff and so on. I think it's the layer 2, and but I think that there are no big issues to guarantee that could be happen. So I would say. But I think we have to be more precisely what kind of security issue could happen. Maybe I think it's maybe encryption, for example. That's right. So can the data be encrypted in the cluster? Yes, it could be. So there is the possibility to encrypt the underlying underlying, how to say, hardware, or the underlying ECS and EFC, elastic file system. So there are possibilities to encrypt that, but not. So the first step is not from our side, because the data itself is not in a readable format on the file system. That means whenever someone gets access to that, it's not possible, or he will not be able to read that, because it's a binary format and it's not a readable format at the end. Okay, hope that helps a little bit, but there are so many questions regarding security, so I think it makes more sense to talk about specific types of issues. So yeah, could you please provide a README file with some hints for the demo repository, bookstore demo JCON? Is there something special you want to know? Just so, because the bookstore demo, I guess it's a Spring application, if I'm right. So you have just to check out the project and you run it kind of like a Spring application. Let me just double check. I'm not 100% sure, but let me just check if there is a description already in place on the bookstore demo.
So the bookstore demo I used before at my GitHub site is just a smaller version of the big one. I put the link in a chat. And this bookstore demo has a README file and JavaPRO and so on.
Florian, we cannot hear you.
Yeah. Can you please?
Okay, is it better now?
Yeah. Now it's better. Yeah.
So the demo I showed is just a smaller, scaled down version of the big bookstore demo. I put the link in the chat, and this one comes with a README and more JavaDoc and so on.
Yeah, that would help. Okay,
Yeah.
Thank you. Another point will be there is today in the evening my workshop, and within that workshop I will share a lot of stuff on my repository and a lot of training project and so on. Maybe if you want to take part, so you will get more information then on the workshop then. Okay, so I hope I answered all your questions. That's all from my side. Yeah, I would say that's it. I wish you the best for the next upcoming topics, and see you then today in the evening. See you. Bye.